Hello and welcome back for another day of 115. It's good to see all of your smiling faces and okay, well, maybe not that. Hopefully you all are doing well, are staying healthy and everything else. In a bid to make sure that this is the least watched video of all time, just to make clear to everybody, just a reminder, while we're going to be talking about all of this work on encryption and how to use the libraries that we sort of discussed a little bit in the lecture videos today, for the purposes of 115, you're not going to be expected to actually be able to write any of the code that I'm about to talk about. It's not that this code isn't interesting or potentially a lot of fun. It is. It's more that it's actually really, really difficult to do correctly, and misconfiguring or making a mistake on encryption or writing code using encryption can actually be worse than anything else, because then you feel like things are secure when they're not actually secure. So just to make sure that, rather than really stress you all out, there's not a lot of time left and everything else. All that we're really worried about as far as this encryption and other work goes is sort of that big picture ideas of how these things work. But at the same time, because honestly, at least for me, maybe for some of you, I actually think that some of this encryption and stuff is kind of cool. I do want to show you how you could incorporate it into your own projects and code, because it's kind of fun. So, what I have right now is, and what we're going to talk about today is sort of the chat app 2.0. So just to get started, what I have on the screen right now is the HTML file that we're using, the web page that we would have. So you can see it's a standard web page. We've still got to send a message. We're going to have our message input area that we can type, our message into, and then two different buttons. One saying send unencrypted, one saying send encrypted. And what they differ on is what function, JavaScript function, they're going to call when they get clicked. So one will call send plain text message, the other one send encrypted message. And then beneath that, we will have just two divs, one for all of the public content, all the plain text content that got sent, and one for the private content, any encrypted text that got sent, just so we can see the difference ourselves. Up here in the head region, you can see that, again, I've got that ajax.js file I wrote that just has the ajax get and post message functions. And I just moved those out because if you haven't noticed, I've reused those over and over again. And so it makes my life easy. I actually have a second second JavaScript file now that I've created. This one's HTML manip for manipulation. And that just has some of the functions that I've been using over and over again, like to get the value of an input and then clear it out and return it. Also, I realized I was frequently taking arrays of text, jamming all the text together with breakpoints between them, with lines each on their own line, and then setting the value of a div to that. So I felt like that should just be in its own function. Also, you can see them right here. These are standard DOM, document object model functions. And by having them in their own file, it makes it easy for me. Honestly, it makes it easy for me to make all of these REPLs as we're going through everything, so I can just reuse them. And, that's something that, honestly, as a not only as a faculty member, but before that as a programmer, I did a lot of. There's a lot of times where there's some code I would want to use over and over again, or I'd want to be able to make very portable. And so the more I can get into these very common functions, the easier it is. So we'll also have the frontend.js. That's where I have all of the JavaScript that's going to be handling sending encrypted messages, or not encrypted messages, depending on the case, over to our server, over to Python. And then the last thing you see here, the one big thing here, is this script tag. And this is where we're loading up the library that's going to actually do the work of encryption. So again, all of this encryption work, whether you're dealing with what we're going to be talking about today, which is public key encryption or shared key encryption, it's really, really difficult to get correct. There's a lot of emphasis on both getting good encryption algorithms out there, but there's also a lot of money in breaking them. And so they've gotten really good, and you'd be amazed at the tricks that people have found, the ways that people have found to hack into systems. We're going to actually talk about them, one way of attacking a system later on that you can use. Well, we'll talk about how it's done. We'll talk about the details. Sorry, guys. But I mean, I remember like one thing, there's all sorts of tricks, ways that you can play around with timing, ways that you can play around with sound. It turns out if you have a good microphone near somebody's keyboard, you can actually figure out their password that way. All sorts of tricks. So whenever you're doing any of this sort of work where you actually have data you want to keep secret, if you're doing it for yourself, have fun with it. If you're actually trying to keep something secret, make sure you use an existing, really bulletproof, bullet-tested, hardened algorithm and library to avoid all of these common bugs that can occur. So we're going to be using NodeForge. You can see it right here. This is just the place to get it. It's one of the more common ones used for JavaScript, so it's fairly useful that way. And then the other big thing in this file, you can see again, we've got the body on load, and for, I don't know, whatever reason, I decided to break the onload into two separate functions. There's two things that we're going to have to get when this app starts up for the client side. We need to get the public key from the server that we're going to be using to encrypt messages. And then we want to get a list of all the messages. So I could have put this into one function. I just split them up into two. So you can see I've got two function calls here in my onload. This is perfectly legal, right? When we have that onload property, the value that's associated with it just needs to be JavaScript. It's just going to execute this JavaScript, whatever it is. If it happens to be multiple statements, that's fine. So to show you the front end, so the get key and get message that I was just referring to are pretty simple. They're just going to send AJAX get requests for the key and the messages. The messages is just going to call display contents. We'll print out right to the console what those that response is, that JSON blob, just so we can all see it. And then what it's going to do is that JSON blob is actually an object with two keys, public and private. Each key is just going to have an array of strings. We'll throw them into their respective locations. So we'll display them properly. The more interesting thing is where we're dealing with all of this encryption work. So for the public key, when we get the public key, what we'll do is it's going to go here. It's again going to come as a JSON blob. That's how we transmit information between the server and our client. So that shouldn't be a surprise. So the first thing that we do is we have to call json.parse. We have to turn that JSON blob into usable JavaScript data. We're going to read in that key in a variable pk. It's going to be value associated with something called key. And then what we need to do is that's going to be, and you'll see this in a little while, that uses this PEM format. So we're going to need to tell the library to convert that PEM format into the actual public key that we can use for encryption. And we do that through this command forge.pki.public key from PEM, and then we pass in the contents of that PEM file, the contents that were sent to us by the server. And we're going to store that in a variable server public key. You can see I actually have it declared up here at the top outside of any function, so that way we can use it across throughout the entire time in this app. So the easy case is when they want us to send a plain text message, an unencrypted message. In that situation, what we'll do, get the contents and clear out the element with the ID message. We will create our object with that plain text. And note that this is an object. It's got a text key that I'll set to plain text. And I'd thought about, and I still have support for, though I haven't actually done, the ability to have the response also encrypted. Now, if we wanted the response to also be encrypted, we would need to send our public key to the server. So I have this key here. Right now, I just leave it as null. That's a special value, meaning basically none. But this way, if I ever wanted the traffic to be encrypted in both directions, I could do that. Honestly, decrypting traffic on JavaScript, encrypting it on Python, which is the part I'm not doing right now, it isn't very interesting. It's just taking the functions that we're doing and sort of throwing them in reverse. It's not particularly important, so I didn't worry about it for right now. Once we have that object, we need to turn it into a JSON blob, and I'm going to log that out just so we can see the difference between the plain text message that we send and the encrypted, the ciphertext that we send. So then we'll call AJAX post request and display the response, the contents. The much more interesting case, of course, is when we have an encrypted message. So that's down here, send encrypted message. So again, we're going to start the same way. We're going to get the contents of our message element and create the object, that send object, turn that object into a JSON blob. I'm going to, again, log that out. But then what we need to do is encrypt that JSON blob. We're going to encrypt the whole thing. It would be possible for us to just encrypt part of it, but it's kind of silly and wasted. At the point we were encrypting, we might as well just encrypt all of it. I figured it actually makes it easier to write the code. You know, the only thing that reveals is, hey, we're sending an encrypted message, which they knew anyway. So there's not much there. So we're going to call this encrypt function and pass in, the JSON blob and our public key. And that's going to come up to here and encrypt. And so what that's going to do is that's going to use our public key. It's going to call the encrypt function. We say, here's the message. It knows what key to use for the encryption. That's the value of key. But then we also have to tell it what protocol we are using to send this message. So it knows how to turn that into a proper thing that can be sent over the internet. So we'll talk about this more because you'll see it a lot more on the Python side, what that exactly does. But what this is this is saying when we encrypt it, we are using the RSA algorithm. That is the primary, the original, and still one of the stronger public key encryption algorithms. RSA stands for the last names of the people who invented it. Revest, Shamir, and Edelman. They were professors at MIT and I can't remember, a university in Israel, if I remember correctly. 3 professors. They were the ones who came up with the first really well-known, I guess not the first, the best most well-known public key algorithm. I guess the first algorithm for public key encryption as opposed to hashing. They've done a lot of other things in their careers. It's also where we got the canonical examples now of Alice and Bob trying to send messages to each other with eavesdropper, spying. The other part of this is OAEP. This is the protocol that we're using. This is saying how we're going to have the messages sent over the internet, over this connection with AJAX in order to be able to see it. And once that's done, what we're going to do, I'll show you what that encrypted message sort of looks like. But now that encryption, when we encrypt it, that is going to be in binary, the language that computers use, the zeros and ones. And that's great for the computer, and that's great because it's needed for this RSA process to work. That isn't useful for JSON. Remember that JSON has very limited types that it can encode. So in order for JSON to encode this, we need to turn that binary array, that bunch of zeros and ones, into a string. And so to do this in JavaScript, there is a built-in function B2A that takes in the zeros and ones and returns a properly formatted string. In order to do this, it's going to play with it. It's going to make some tricks, some hacks, you'll see. But that's what we need. That's valuable, so that's useful for us. And we'll return that string that's representing the encrypted text. You can see to decrypt, I already have the functionality here, even if I don't have that. It's not very interesting. It's just calling decrypt. So once we have the encrypted message, we'll log it, send that over. So that's everything on the front end. We also need to talk about what's going on in the back end. The easy part is the back end, the Python that's actually doing the data input and output. You can see I'm going to create a database just to store all of this. I'm using a database because it's easier and faster, honestly. There's no reason why I couldn't use text files like we did before, but you wouldn't do that. You'd use a database. I'm going to have two tables in this database, one called public, where all the unencrypted messages went to, one called private, where all the encrypted messages go to. And because all of the encryption is really about the traffic between our clients and the server, there isn't really anything that needs to be in this back-end code to deal with the encryption aspects. You can see the one thing I've done is I've started to try to clean up the code a little bit. You can find a link on the course webpage to this REPL. I'm just trying to make it a little bit nicer. So part of what I have here is add message to table. Since the work of adding the message is the same, whether it goes into the public table or the private table, the only thing that changes is the name of the table. I just threw that code to insert it into this one function, made sure that I remembered to call HTML escape to make sure that we can't be hacked through an HTML injection. And that way my code looks a little bit better. Same thing for getting all of the messages, whether we're getting all the messages from the public or private table is the same. So I just have my select star here, and I can call this from either one of the functions I have for getting the public message, getting the private message. If you look, I have this question, why is this such a horrible practice for all private messages to be working this way? Right? Realize that this isn't actually a particularly secure application. We are using encryption to send messages back and forth. But of course, as soon as we get to the server, I decrypt it and store it in its decrypted format. So anybody who really wanted to spy on these routines, there's an easy way to go about it, rather than doing, all they would have to do, honestly, is just look through the database on the server, right? They don't have to worry about trying to break RSA encryption. That'd be really difficult. They could just hack the server and be okay. So all of the really interesting work is going to be in main.py. So, we have some pretty simple parts. We have, returning the HTML file, dealing with all the JavaScript files. Another thing we have to do, right, in order for this to work, we have to be able to send that public key to anybody who wants. So we serve up the public key in this function. And so to do that, we're going to read in the contents of that public key file. And actually that needs to be not just normal, but we need to read it binary format. We can print that out. Turn that result into a JSON blob, send that back. Then the more interesting thing is at the beginning, what we're going to need is, our database, but also our public and private keys. And right now what I have it set up to do is to read in that private key at the very beginning and keep it around in memory. This is actually very, very bad practice. Again, it does save us some time not having to read that private key file each time, but it's really kind of slow. So just to show you why you may not want to do this, I'm going to start this up right now. And you can see there's a noticeable pause because it has to actually spend some time generating all those keys. And it's not, there we go. So once it's done, we're okay. It doesn't like that being RB. Now that I made that change, does need to read it in. Oh, that's right, because I changed how it's written out. So if we do this, you can see again, noticeable time in order to create those keys. And the reason why is what it's doing is calling this function here, generate keys. So what this is going to do, right, the first line here, I'm using that Pi Cryptodome library. First thing we're going to do is call RSA, that's the encryption algorithm we're using, .generate 4096. This is going to generate a key, a pair of keys actually, that are 4096 bits long. So 4096 zeros and ones. Obviously, this is pretty huge. In human terms, since most of us don't work in base 2, these are numbers that are going to be about 1,234 digits long. So really, really, really huge prime numbers. And actually the way that cryptography works, the way that the RSA algorithm works, is actually pretty interesting. It's using some properties of prime numbers and the fact that if you have two numbers that are relatively prime, by using some fancy math, we can have this public key and private key combination. It's kind of a neat trick. So once it generates those keys, what we're going to do is write out the public key and the private key files. And I realize you don't see them right now over here. If I reloaded the page, you would. But what we're going to have to do to get that public key, we call myKey.public key, and then we can say export it as a PEM file, write that out. Then we get the private key. Can I teach you a little bit of hacking skills to check if you've been hacked or not? If you've been hacked and the person is anything competent at it, you're not going to find out. Can I teach you a bit of hacking skills? I'm not sure exactly what you think that's going to be. Honestly, the way that, we sort of talked about the main ways of hacking last time, the HTML injection, the SQL injection, that's usually what we do. Encryption is really just a way of keeping messages private between the server and our clients. And the answer is, if you've sent anything in plain text, it's been read. This happens all the time. There's absolutely no way to detect it. You're pretty much out of luck. To be honest, even if you send something out with RSA encryption, for instance, right? This is really just relying on the fact that we have a pair of 4096 bit long prime numbers. Now, there are only a limited number of prime numbers. Admittedly, if we're talking about any prime number up to 1,234 digits long, it's a large number of prime numbers, but it is still a set of prime numbers. So if somebody wanted to, right, the public key we're going to share that around. The private key we're going to keep private, but somebody could just start trying every possible prime number until they get to the one that decrypts it. Can they do this? Well, yes. I mean, honestly, it's just math. Now, the trick is that by using a key this large, we're going to make it really, really expensive for them to do it. It's going to take a lot of time, which is to say money. I mean, potentially years upon years upon years for them to be able to generate this private key. So in that sense, can they do it? Yes. Are they going to? Well, not for this program, right? No one cares about the messages that we send, particularly since we send them back in plain text. No one's going to try to hack this ciphertext. On the other hand, if it's my banking app, my wife actually just got sent a paycheck, so I am going to, after this is over tonight, my wife, probably one of us, will end up taking pictures of the check and using the app to send it over. Well, this is going to go over the web. Guess what? Now, that's a paycheck. If you can hack that, if you can hack that key, yeah, I mean, there's my wife's paycheck, but there's a lot of them out there, right? Big bank. There's a lot of money in it. Is there any way to tell if you've been hacked? Well, no, again, it's just math. If they can read it, they can read it. There are tricks that we're going to talk about. And actually on Friday, we're going to talk about authentication, how to make it much, much harder for people to fake it, how to create login systems and that sort of thing. But again, all that we're doing with any of this encryption is we're making a game. We're making it really, really, really difficult for people to hack this system. The only way to keep things truly private is to prevent them from ever seeing it. As soon as they've seen it, if they want to, they're going to be able to get access. Now, again, for anything that we're writing right now, does it matter? No. I teach the software engineering class, so these are seniors. For the work that they're doing, does it matter? Probably not. I mean, they're actually making some real projects. There's certainly real systems I've used that will have that. It is possible. But, no one's going to spend a couple of years to find out some of this information. By the time they do, the point is moot. On the other hand, there have been a couple of incidents over the last year where a foreign country has accidentally, and when I say accidentally, I don't actually mean accidentally. This was obviously an intentional action, redirected all of American traffic, literally the entirety of internet traffic, to be rerouted through their computers. Why were they doing that? Oh, they were almost certainly trying to get access to all that data to hack it. And so some of that data, it's been exposed. That's, what exactly? We don't know. What are they doing with it? We don't know. Hopefully it'll take them a long time. That's why we do all this, but it can happen. So when we start up, right now I'm reading the private key. You would never actually want to keep the private key in memory. There are attacks that you can do on a shared cloud server, such as Replit. There are ways, even though each part of the cloud, each person is being kept separate. In theory, anything I do in my REPL shouldn't affect what you're doing in your REPL. There actually are ways and attacks that might be able to expose some of that. So normally we would not want to keep the private key in memory for longer than is absolutely necessary. At the moment, however, I am actually reading it in at the very beginning, mostly so I could show it to you. So what the private key looks like, the private key file, is this. You can see I'm going to print out private key and print out what that thing is that we're reading in. And it is just a series of bytes, zeros and ones, that the computer understands. Very close to text because it's something it needs to use. So you can see when we print it out, this is actually what we're getting for our private key. It hopefully looks like almost pure garbage. To some extent, that's true. But in reality, what this is a this is a way of encoding one of those huge numbers. And that number is what our server is going to use to decrypt the message. In addition to this private key, you can see what we're going to do is we're going to call this PKCS-OAEP. This is saying how we're going to handle the protocol that we're using for messages. In particular, what this protocol defines is how messages are going to be sent. One way that we could attack and defeat encryption is if we had messages of varying lengths. If we could figure out short messages from long messages, use that to sort of try to figure out what's going on, this would give us a way of potentially breaking the system. So one thing every protocol does is it makes sure every message that gets sent out has the exact same length. Now, for longer messages, what does this mean? For longer messages, this means that what we're going to do is break them up into a series of messages. And then for that last message, or for shorter messages, we actually pad it out. We add some garbage at the end just to keep everything the same length. And so that OAEP, that specifies how we pad it out with some of that garbage text, how we make sure every message is the same length. And that result, that's going to be this RSA key that it's going to take in. That's what it's going to be using. So at that point, the question is, well, what kind of messages are we getting in? So let's try to actually do this, right? You can see the public key here that gets requested by the clients when they start up. It's not particularly interesting. It kind of looks like the private key. Again, it's a number that's being encoded, just a little bit different, right? Just a different number. So if I want to send a message, I can send it unencrypted. And you can see when I do, what we're going to send out is this JSON blob, text with the message hi. Key is null because I just left it null. And you can see the response I get back was that we added hi in that private area. This is on the client side. If we look on the server side, you can see that the server, right, it's going to come in as a plain text message. We'll read in that JSON blob. I printed out just so we could see it. Convert that JSON blob into usable Python data. That it's going to be, in this case, a dictionary. Get the message that was sent over, get the results of the value associated with that text key, and add it as a public message, and then read it all our messages, send it back. So if I send that same message, that hi with an exclamation point, but now I send it as an encrypted message, you can see it looks very, very different. So again, we start as that same plain text object, because it's the same basic idea, but then we encrypt it. And so you can see when we encrypt it, we're getting all that binary data, those zeros and ones, not something that can be added to JSON. This isn't a string. And in fact, it includes lots of these weird glyph marks. If you look, this is a place where the number that's there, the zeros and ones that are there, don't have a character that can appear, don't have an encoding in this font. So in order to make this usable, we have to use that B2A. We have to turn it into text. And so our ciphertext, that encrypted message that we're going to send, is this whole thing over here. Still not particularly easy to read. You can imagine this is pretty big. This is a lot bigger than that simple message because, again, we're padding things out, making sure that everything is the same size. And then you can see when we get it back, we get the same, we get now both hi was added as a public message, and now just recently hi was added as a private message. If we look on the server side, someone is just connected to this. One of you is just connected to this app. You can use this just as easily if you go to the URL. You can see that it received that whole big thing as a ciphertext, right? This is the message it received. And what we have to do is call this base64.b64.decode. This takes that text, that ASCII, and turns it into binary. You can see the result of this is a series of bytes. We then use our private key to decrypt those bytes, and this is using that, the code provided by the PyCryptoDome library, very well-known secure library. Now that we have that message decrypted, we again have to decode it, turn it into ASCII, turn it into text. And, well, what is that text? Well, we happen to know, because we worked with this before, right? We sent it, that text is a JSON blob. So we're actually going to convert that JSON blob back to a regular usable Python data, get the message out of it, and add the private message. And as I say here in the comments, using this regular structure isn't always the best idea. With RSA, it shouldn't be too bad. It does give, however, attackers a little bit of space since they know some aspects of the message. Depending on what you're doing, if there were a weakness in our encryption algorithm or the way it was implemented, this would give them a way of potentially a leg up in breaking it. Part of what the Allies did, actually, during World War II, one of the first computers was used in breaking the Enigma cipher, the encryption that the Nazi Germany was using. And one of the ways that the team in Britain, Bletchley Park, were able to break every day the algorithm would change. Part of how Bletchley Park was able to break the German encryption is because it was during Nazi Germany time, every message ended either with HH or Hail Hitler. It was Nazi Germany that was theoretically appropriate for Nazi Germany. And so this gave them a way to exploit. They knew what to look for near the end. So ideally, you wouldn't necessarily want to do it this way, but anybody who's trying to break these messages, all they have to do is wait for the response to come back. So once we have that, we send the response. So the last thing I just want to show you is part of what is so important about encryption. One of the things you want to do is you want to maximize what's called the entropy of your ciphertext. So ciphertext is the encrypted text. And when we talk about entropy, we mean the level of randomness. One thing you don't want to do is for small changes to be very visible. You want each message to look different in a way from the next. So this is still math. So if I send the same encrypted message, it's actually going to look a little bit different because it's not a full message. You'll see the ciphertext changes because that garbage that we added at the end changed. If I could figure out the exact right size, it would be the same. But if I make even just another small change, you can see it's going to be completely different, right? Going from an exclamation point to a period, this ciphertext looks completely and utterly different. You can't just go by one or two characters and figure out what the original message was. In order to understand the original message, you need to have that entire ciphertext and hack the whole thing. This makes it a lot more difficult to defeat. So the one last thing, when I think about it, is at the beginning I said we don't really want to keep our private key in memory. We would never actually do this. Instead, what we'd want to do is every time we want to decrypt it, reread it from that file. So in order to do that, I need to add this here. The reason why people usually don't do this, let me clear this off, is because of time. Actually, if I thought about it, I also could, once we have those key files, we do not need to regenerate them. I can get rid of that. So here I'm going to reload this up. And I just want to point out, if I want to send an encrypted text now, where I'm going to have to reread the file, you can see that it works just as well. We get the same ciphertext. But that response was pretty much instantaneous, right? There is no noticeable delay for doing the right thing. So there's never a reason at this point, certainly for something like we're doing, for not doing the right thing and making sure that private key stays private by not only never sharing it with anybody, but also only reading it when it is absolutely necessary. So hopefully this gives you an introduction to how we can code with these encryption algorithms, how we can use these systems to write stuff on our own, give you a chance to play around with it. Like I said, if you're ever doing a real application, probably this isn't enough if you're really trying to protect money or any of that sort of stuff. But if you're just doing it for fun, and at least for me, I think of this as being really, really fun. This gives you enough to get started to really play around with it. Like I said, on Friday, we're going to do a little bit more. We're going to talk about how we can use this along with cookies to perform authentication, to create systems where people can have usernames and passwords and have to log in and actually be able to track them when they're logged in, the same way that Replit or YouTube or Amazon or any other website does. But other than that, any other questions people have? Okay, I don't see any questions. So thank you all. Hopefully you can stay safe, stay healthy. Hope you have a little bit of fun. And I will talk to you all on Friday. Bye.